parameterized complexity, but the notion of fixed parameter tractable algorithms. So, am I audible? Yeah, okay, good. Okay, so parameterized problems come with, this is input and this is sometimes there need not be even one parameter. You can have a tuple of parameters. You just combine them all and think of it as parameter. And you are interested in, so your problem, you are interested in some decision question and your problem is fixed parameter tractable if, so the problem, whatever your question, so it's, the important thing is this is independent of k. So I have an algorithm with this kind of a running time. Okay, so you can think of it as some sort of a multi-dimensional analysis of the problem. So, instead of just looking at the input size, you have the input and various other parameters, and you play around with how the complexity of the problem depends on these multiple different parameters. Okay, so typically we will be looking at hard problems, but sometimes we will also look at problems which are solvable in polynomial time. So it need not necessarily be working with hard problems. Okay, so even in a problem which is solvable in polynomial time, we may want to improve from n square to order n, and we ask if some parameter is small, can I get something better than n square? So it need not be restricted to just hard problems. It's a general multidimensional way of looking at problems. Okay, we saw some examples of these parameters. Could be degree, solution size, some distance to some nice class, nice instance. So you can, that also makes this theory very rich, that you can define parameters which make sense in practice and then study your problems. Okay. So towards the end, yesterday I was giving you an FPT algorithm for a version of the SAT problem, max SAT problem, and the way we actually did it is by somehow reducing the input size to a function of k. Okay, so remember the problem was max 3 SAT given a 3 CNF formula. Is there an assignment? Is there a 0-1 assignment to the variables satisfying at least k clauses? This is a standard decision version of the max SAT problem. So not even actually 3 SAT, right? We looked at even the general CNF SAT problem. And the way we designed our FPT algorithm, we said, oh, first observation is that you can show that m is at most 2k. And then we did some pre-processing. We managed to show that n is at most 3 power m, which in our case is at most 3 power k. So that means I have managed to reduce the input size, which in our case consists of this m and n, to a function of k. Then after that, you can use any algorithm to come up with an FPT algorithm, because the running time now would be just a function of k, because your input size is bounded by a function of k. So this is one nice general technique to show some problems fixed parameter intractable. What is the technique? Somehow do some pre-processing, reduce the input size to a function of k, bounded by a function of k, then you can do some brute force on that, right? Now this is nice also because pre-processing is something really in practice people do all the time. Okay, just get rid of some redundant stuff and then work with hopefully some small size input, and then there you do some brute force kind of thing. It's a natural thing, somebody is implementing the algorithm. It's in algorithm engineering, you'll do some, let's get rid of this, get rid of this, get rid of this, and work on something small and do some brute force. Now, without parameterized complexity, it's not even very clear how to analyze such pre-processing algorithms, because in general, if I give you an NP-hard problem, right? So if you have pi is some NP-hard problem, and x is some instance, okay, remember that this pre-processing we did was a polynomial time thing. We did not spend anything exponential. We did not make use of this FPT running bound relaxation. We just spent polynomial time and somehow reduced the function input to a function of k. So the question is, suppose I have an NP-hard problem, can I reduce this in poly time? Okay, so here I am not talking about parameterized problem. There is no parameter. It's just a standard take your Hamiltonian cycle or click or vertex cover problem. In polynomial time, can I get an equivalent instance x prime? So this was an equivalent instance, right? That's what they did. Can we get x prime is equivalent to x? What does equivalent means? That if it's a decision question you are working on, S if and only if x is an S instance, if and only if x prime is an S instance, with the property that somehow cardinality of x prime is strictly less than cardinality of x. Is it even possible? For a general NP-hard problem, I have a standard regular input. Somehow in polynomial time I have some pre-processing routine which will always reduce the input size by even 1 bit or something. Why is it not possible? I'm not saying that it will always be possible for every problem. Suppose for some problem I manage to get rid of some redundant parts of the input and reduce the input size, but I am able to do it for every instance. What happens?
You can always reduce by 1 bit. You can keep applying the same.
Keep applying the same thing, right? So I have an arbitrary instance. In polynomial time, I reduce the input size to some equivalent instance, but the input size is smaller. What stops you from applying this again and again and again until you have only 1 bit and you get the answer, right? And you only spend polynomial time because the size of x is reducing, so you won't do it more than size of x times. And so overall you have solved the problem in polynomial time, so you don't expect that because it's an NP-hard problem. So in general, for an NP-hard problem, people always do pre-processing, but we don't know how to come up with a nice theory to capture this. But parameterized complexity with this additional secondary parameter has a nice way of capturing this, and that is this notion of kernelization. Right? When I turn this on, is there a problem? So this is not possible. For every instance, being able to reduce even by 1 bit is not possible for an NP-hard problem, but somehow we want to capture this notion of pre-processing, and that takes us to this notion of kernelization. Right? This is something we did, for example, for this SAT problem. What is it we did? Okay, so kernelization is a polynomial time algorithm. Okay, kernelization of a parameterized problem is a polynomial time algorithm. Right, it's poly in size of x and k for an instance, which to another equivalent instance. So equivalent means, as I said, we are working with decision problem. It's an S instance if and only if that's an S instance. And more importantly, cardinality of x prime is and also k prime are bounded by some function of k. Where f is some function of k. So what we did was this kernelization for the Maxad problem, where we did some polynomial time pre-processing. To the pre-processing was that if two variables have the same snapshot in the formula, we got rid of both these variables. That was the pre-processing we did. At the end of it, we argued that m and n are bounded by some function of k. Okay. So if in polynomial time you can reduce your input. So now we are not solving the parameterized problem. Okay. All we are doing is, given this parameterized problem, we are reducing to an equivalent instance where the input size is just a function of k. If I manage to do that, such an algorithm, if I can manage to do that for every instance of the problem, such an algorithm is a kernelization of the problem, which means that somehow kernel corresponds to some meat of the problem. We've gotten rid of some redundant stuff and now we have something core of the problem. And x prime is called the kernel, and the size of x prime is the kernel size. Now in practice, this k prime would be typically less than or equal to k. So imagine what I'm doing. Let's look at the vertex cover problem. I have a graph and I want to know whether there is a vertex cover of size at most k. Somehow in polynomial time, I produce another graph which is an equivalent graph, equivalent meaning S if and only if it's an S, such that the new graph, the number of vertices and edges is a function of k. There's no n at all, right? If you had million vertices and I want to know whether there is a vertex cover of size 25, then in my new graph, the number of vertices is just some function of 25. Quadratic, cubic, whatever, something like that. So it's just hopefully some small function of k. And in that, I am asked to look for a vertex cover of size k prime. So G has a vertex cover of size k if and only if this G prime has a vertex cover of size k prime. Such a reduction is what is called a kernelization algorithm. Typically, usually this k prime would be smaller than k. You are looking for something of size at most 25. I might have picked something and now you have to look for a vertex cover of size 15 or something like that. But in the definition, we will allow it k prime to be even a function of k, could even be larger than k. So now the following is immediate from this definition. Okay, so if pi has some algorithm Pi is some parameterized problem. I don't care about the running time of the algorithm. To answer the instance x comma k, I have some algorithm. Okay, it's not an undecidable problem. That's all I'm saying, right? Undecidable means no algorithm. You have some exponential, double exponential, triple exponential kind of an algorithm, which given an x comma k will answer it, and has a kernelization then pi is FPT, right? And I defined FPT, and now from now on, most of our goal will be to design fixed parameter tractable algorithms for a large, different kinds of problems. So here is one tool I'm telling you to show some problem is FPT. So what is it? Suppose you manage to give a kernel for this problem. In polynomial time, I've reduced to an equivalent instance where the input size is a function of k, and if pi has some algorithm to answer, then you get an FPT algorithm. Is that clear? Why? Yep. You're the only one who is seeing it for the first time. They all have seen it before. So Kaustubh, is it clear why? What is the proof of this?
Because you can solve the kernel size is empty, so you can do the same algorithm on that size.
So give me the FPT algorithm for pi. What do you do? So you are given an x comma k. So what? Yes. So you apply the kernelization algorithm to get an x prime k prime. This takes polynomial time. And then after that,
because the size is 58 of this instance,
yeah.
we can apply the same algorithm which we applied on the original.
Which algorithm? No, the origin. I mean, this doesn't solve the problem. This polytime algorithm only give you a reduced instance. Now I have to find the answer for this. I have some algorithm for pi, right? Apply that algorithm here, right? The only thing is I don't know the running time of this. This could be really exponential, double exponential, but doesn't matter. X prime size is f of k. So doubly exponential, triply exponential of f of k is another f of function of k. So you've spent polynomial time plus some function of k. That's all. So it fits into this kind of a running time. A pure polynomial time to do your kernelization. After that, we just apply some whatever algorithm we know. We'll see some examples quickly. Okay. So the important thing is that here is one. So if you can give a kernelization for the problem, you can immediately show it's fixed parameter tractable. So now the interesting thing is what would be the size of the kernel? How small a kernel can you get? So this is up from here to here is a pure polynomial time, n square, n cube, linear, n plus k, whatever. Okay, there is no exponentiation at all in the runtime. After that, there will be, this could be a bad algorithm, but it's a bad algorithm on a function of k. There is no n here, so that's fine. So that gives you this kind of an FPT algorithm. Okay. Now another really interesting thing is that the converse of the statement is also true. That if somebody has given me an FPT algorithm, may not be necessarily through a kernelization argument. He ran some algorithm, some branching algorithm, something, and got an algorithm of this kind of a running time. I can also produce a kernel. Okay, that's very interesting. That also means that now these two notions are somehow equivalent. A problem is fixed parameter tractable if and only if it is kernelizable. Okay, so let's see the converse. Also note that if you have FPT through kernelization, your running time is actually of the form f of k plus n to the c. Right? It's not f of k times n to the c, because this is a pure n to the c, and after that it is some f of k. Okay. Now I am saying that, oh, any FPT algorithm, any problem which is in FPT has an algorithm of this kind of running time. Okay. So why? If a parameterized problem phi is FPT, then phi is kernelizable. So kernelizable means what? That in polynomial time I can produce an equivalent instance where the input size is bounded by a function of k. That's what it means, right? We're talking about function of the parameter, whatever the parameter is. Who knows the proof? You do, okay? Okay, so suppose phi is FPT with an algorithm whose runtime is f of k n to the c. Okay, c is independent of k. Now I have to give you a polynomial time algorithm which will convert an instance of pi to another equivalent instance of pi. Okay, so one more thing. So our goal is to answer whether xk is an S instance, right? This is what the problem. You're given an input, a parameter, and we have some decision question. Is it an S or no? Is there a vertex cover of size k? Is there a dominating set of size k? Right? Is there a, so that's the kind of question I'm interested in. Now, in the kernelization algorithm, along the way may actually answer the question also. It may say no, it is not. Okay, somehow it might figure out that it is not, or it might say yes, it is. Okay, so in that case, just to fit with the definition of kernelization, what do? I have to produce you an instance x prime and k prime, right? So I'll produce a trivial S instance or a trivial no instance, and that would be my kernel. Okay, so if along the way if you actually found the answer 0, yes it is, no it is. Suppose it's the dominating set problem and you found out that yes there is a dominating set of size k. Now to fit with the definition of kernel, I have to produce you an instance, a graph which has a dominating set of size k. Is it that hard to come up with such a graph? A graph that has a dominating set of size k. You create one and say this is your kernel. Right? Similarly, if you want to give a graph which has no dominating set of size k, you can trivially generate one and give that as a kernel. Okay, so this is, I could extend the definition to say along the way I might say yes or no, or produce an equivalent instance, but these are equivalent. Okay, so pi is fixed parameter tractable. Somebody has given me an algorithm which runs in f of k into the c. So now what is the kernelization algorithm? So what are you going to do? Okay, so run with an algorithm A, right? So run A for n to the c plus 1 steps. You're going to laugh if you see the proof. Right? It's just trivial. It's some bookkeeping.
I have a proof using this.
Using what? So tell me that. Okay.
You run the same.
Okay. Yeah.
To the c by 2 steps, then you will get that f of k is greater than or equal to power of n.
Okay. So run A for n to the c plus 1 steps, right? I have this algorithm which takes your input x comma k and give you an f of k into the say c steps, yes or no. It'll actually solve the problem. So now I run it for n to the c plus 1 steps, right? So here is my algorithm which takes x comma k and either it will say yes or no. And the time it will take is f of k n to the c. Somebody has given me that kind of an algorithm, right? So now I'm going to run this for n power c plus 1 steps, right? So I take my x comma k, run it for n power c plus 1 steps. Okay. Now one of two things happens. Maybe the algorithm actually has solved it, right? Maybe it has solved it and given you a yes or no answer. So either you have solved it or it is still running, right? So you have two possibilities. If it is solved, then you give an yes or no, or like the way I said, you produce a trivial instance which is an yes or no. Suppose the algorithm is not stopped. What does that mean? F of k n to the c turns out to be more than n power c plus 1, right? The algorithm actually needed f of k n to the c steps to give the answer, but you have run it for only n to the c plus 1 steps. So algorithm has not stopped. So what does that mean? In the other case, n to the c plus 1 was not enough. Right? What does that mean? I cancel out the n to the c. That means my n is less than f of k. So you give the original instance as my kernel. Right? I just give x comma k as the kernel. Why? What is the size of x? N, which is bounded by a function of k. Right? So input, and I've spent only polynomial time. There's no dependence on, exponential dependence on anything here. So in n to the c plus 1 steps, either I have a trivial instance with an yes or no, or I will just give the original instance and that itself is a kernel because the size of the input is bounded by f of k. So is that clear? So what this means that these two theorems tells you that it's an equivalent notion. So that means you can write the running time of an FPT algorithm as f of k plus n to the c or f of k times n to the c, it doesn't matter. Good. So now let's get on to designing some kernels for problems, right? So let's get on to examples. And note that at least the purpose of this lecture and on this topic is not really to solve the problem. Kernelization doesn't actually solve the problem, it will produce you an equivalent instance of small size. Okay, so our goal is to produce an equivalent instance of small size and hopefully that, so xk should be reduced to some x prime k prime where x prime size is small. That's our goal. And then to solve the problem, you apply some brute force algorithm, all that. So I'm not going to talk about how you solve after that. Then you apply any efficient algorithm you know on it because you spent only polynomial time so far, and after that you can spend any algorithm you know for that problem. So we already saw this max sat problem as a kernel of size what 3 power k or something, right? 3 power k variables and 2k clauses. That's not the best kernel, you can improve it, but that is at least one example we saw last time. So let's start with again vertex cover, right? So you have and my parameter is k, and the question we are interested in, does there exist a vertex cover of size at most k? So one important thing we're going to make use of it is I'm not looking for minimum sized vertex cover, right? So this parameter can be sacrificed in many interesting ways. This is what Mike Fellows calls it. So we are looking for vertex cover of size at most k, and let's come up. So the way you do it is like some pre-processing, some rules we will apply, and it's important to show that your reduced instance is an equivalent instance of the original problem. If it is yes, if and only if this is an yes, at every step of the way. I might apply some 10 rules, sequence of 10 rules, and you just apply, and finally I will argue that what I have produced is an equivalent instance, it has a small size. Okay. So here are some rules, right? Okay, what is some simple redundant thing on a graph for a vertex cover problem? What can you get rid of? I'm looking for k vertices to cover all edges, and I'm trying to remove some unnecessary things from the graph. So what can you get rid of? Trivially, isolated vertices, no point, they don't play any role in covering any edges. So let's remove step. So clearly they don't play a role in covering any edges. So now what I get is G prime. So wherever you have isolated vertices, this is a clear polynomial time step, run through the graph and find isolated vertices and remove them. We also saw a rule in the first lecture where when you have a degree 1 vertex, you can pick its neighbor into the solution and get rid of it. Okay. But I am not even going to apply that. I don't even need it. Let's see. Okay. I think I don't need it. But now I'm going to use the fact that I'm looking for a vertex cover of size at most k. Right. I'm not asking for some vertex cover, minimum vertex cover, nothing like that. So now if there is a vertex of degree more than k, what can you say? Right, so I have a vertex x which has more than k neighbors. I am looking for a vertex cover of size at most k, right? Suppose I don't pick this vertex into my solution, then who will cover this edge? This vertex, right? Because I need to cover every edge, remember. Suppose I decide not to pick this vertex has to be picked. So all the neighbors have to be picked. There are more than k of them. I lose my budget. I am given only k. So what does that mean? You have to choose this vertex. If there exists a vertex of degree k greater than k, then include x in the solution. Right, so I'm constructing my solution S. So and delete x. So I start with right, x has done its job, there is no reason. So I include it in the solution, delete it, now I have a new graph, right? But my budget is also, I should decrease it. Now in the new graph, I am looking for a vertex cover of size k minus 1. So I will now change k to k minus 1. Right? After applying this rule, maybe some vertices might have become isolated now. Go and get rid of them. Maybe there is another vertex of degree more. So keep applying these rules. Okay. In every step, as long as you are applying the rule, you are making progress, you are removing. So you won't do this forever. Right? Maybe at most n times you are going to do. So this is like polynomial steps. You keep applying these rules. Right? This is the way usually the kernel algorithms work, that you have a bunch of rules, you have to show correct, so I have to show correctness of this rule. Right? The proof of correctness of this rule, that the reduced instance has a vertex cover of, okay, so let G prime is a new graph. Then the claim is which I'm not going to prove, but G prime has a vertex cover of size at most k minus 1 if and only if G has a vertex cover of size. Right? This is, I've now reduced from G and I got in a G prime and I got a k minus 1. So usually, in this case, this is not a very hard thing to prove, but as we design some complicated reduction rules, you have to prove this equivalence of the rule, and that would be quite non-trivial sometimes. Okay, but I'm not going to give a proof of this. It's fairly obvious. And the observation is that any vertex cover of size at most k in G should contain this vertex. That's all the proof will make use of, because, and that's all you're doing. You're doing whatever you are forced to do. Good. So now I keep applying this and I get a resulting graph. What is the maximum degree of the resulting graph? K, right? Because anything more than k, you've gotten rid of it. If you have a vertex of degree more than k, you will not have stopped. You keep applying this rule. So resulting graph has max degree less than or equal to k, because if it is more than k, you would not have stopped. Good. So now I started with my graph G, applying these rules in polynomial time. I've gotten a G prime, and here I have to look for a vertex cover of size k prime. This k prime is k minus whatever number of vertices you already picked. Right? If you picked some 25 vertices, then you are in the remaining thing, you are looking for k minus 25. If already you have exceeded your budget, then you just stop and say no. There is no vertex cover of size k. That could also happen, that this k prime has become negative. Then you say that, I can't cover, there is no vertex cover of size at most k. Right? So let's write that as a rule. If k prime is less than 0, return no. The graph has no vertex cover of size at most k, because I picked whatever I am forced to pick, and that itself is already more than k. Okay. If G prime has greater than k prime into k edges, what can you say? Right? My resulting graph, I have done this, and here I am looking for a vertex cover of size k prime. Right? And each vertex can cover at most k edges. I don't have a bound on the number of vertices yet. I know that I have a bound on the max degree, but if this graph has more than k into k prime edges, then what can you say? There is no vertex cover of size at most k prime here, because each vertex can cover at most k edges.
Right after root 2 you have a bound, because n choose 2 should be less than or equal to n.
Yeah, that's what I'm getting to. Yeah.
Is k prime is less than 0 or order of s is greater than k?
Both are same, right? Because every time I include a vertex here, I drop k.
But k prime.
I should say k. There is no k prime. K is this new k. Order of s is greater than k means what? K would have dropped from k to something less than 0 now, right? It's the same thing. Yeah, you can just say if order of s is greater than k. Right? So this is same as saying I have already picked more than k. Okay, so it's k into k. I'm not saying it like a proper pseudocode, but you get the idea, right? So if J prime has more than k square edges, then there is no way k vertices can cover all the edges because each vertex in the resulting graph can cover at most k edges, right? So you just say no. So now, hence, that this G prime is my kernel. How many vertices can it have? Because the number of edges now I have bounded it to be k square. Number of edges is bounded. There are no isolated vertices. So you can't have too many vertices as well. At most 2 times k square. Right? So G prime k, and let me actually use k prime. Number of vertices is at most 2 times k prime. No, k prime, and number of edges. Yes, this is k, which is at most k square. So what I have is a k square kernel. So in polynomial time, I can, for the vertex cover problem, I can reduce the input size to a function of k quadratic, simply order k square vertices and edges. Now you can go and apply your brute force algorithm to design your FPT algorithm. So what, right? I've not solved the problem, but I've just compressed my input from n to k square. So along the way, as you notice, I might have said no, right? I might have actually solved the problem, and as I said, to fit with the kernel definition, I could just give a graph which has no, what would be an example of a graph which has no k-sized vertex cover? What would be? K plus 1? Complete graph on k plus 1 vertices? No, that will have k-sized vertex cover. K plus 2, for example. Even a sparse graph? K plus 1 distinct edges. A matching of size k plus 1 is good enough, right? You cannot cover it with k vertices. So that would be my kernel. If I have to say no, I will produce some k plus 1 sized matching and say that that is an S if and only if this is an S. I know this is no, so that's a no. No is what I have already found anyway. So trivially I can produce one such thing, right? So I can do this, or as I said, I can fit with the kernel definition to say either I solve the problem along the way or produce an equivalent instance whose size is a function of k. So note that in the converse of this statement we produced, what was the kernel size? I said if you have an FPT algorithm, it is kernelizable. What was the size of the kernel? F of k. So it's typically exponential or even W, F of k could be pretty bad. F of k is clearly not polynomial because you're talking about a hard problem. So your FPT algorithm will have an exponential dependence on k, maybe even worse. So that will give you an exponential kernel. So another interesting question on which there has been a lot of recent work is, even if a problem is FPT, does it have a polynomial size kernel? Right? For example, vertex cover is FPT and I produced you a k square size kernel. In fact, we will improve it in the next lecture, the size of the kernel using some matching theory. One can show that the number of vertices can be reduced to something like 2k or even less than 2k. 2k minus log k is the number of vertices you can reduce to. Okay, so that's another really recent direction on trying to show a problem has a polynomial kernel or does not. There is some machinery by which you can show that a problem is FPT, but it cannot have a polynomial size kernel.
Is there a lower bound?
For?
What size kernel?
For?
General problem.
Yes, not for general problems, for specific problems. Vertex cover, for example, has a lower bound that you can't get k power 2 minus epsilon kernel unless something happens. On the size of the kernel, which means the number of edges, nothing stops you from reducing the number of vertices, which we will reduce next time. Okay. So a related problem which gets considerably harder, and I won't be able to even explain today, is the feedback vertex set problem. The problem is even more harder in the directed graph sense, but let's look at undirected graph. This problem makes sense even in directed graphs, for which we don't even know there is a polynomial size kernel. But let's look at this. Okay, so this is, you want pick k vertices to kill all cycles. That's what is the feedback vertex set. What is a feedback vertex set? It's a set of vertices whose removal makes the graph acyclic. Okay, it makes it a forest. So what is the minimum number of vertices you need? So a vertex cover is a set of vertices whose removal makes the graph with no edges at all. Whereas here now I am saying I don't want any cycles. Okay, so this is considerable. I'm not even going to give you a kernel today. It requires enormous machinery, and we will do it in the 2-3 lectures later. But I just want to illustrate that it's not so easy. Okay, so what are some rules you can do? Like vertex cover. I can remove isolated vertices. What else can I do? Cut vertices. You can remove cut vertices, but they can cover cycles, right? It may be part of, so you can break it up into connected components or even two connected components, but you can't remove cut vertices. Cut vertices can play a role in covering cycles.
In the covering set, keeping into the covering set.
Oh, that is also not clear. Does every cut vertex, should it necessarily belong to the covering set? We are trying to find, is there one of size at most k, and you don't want to do anything suboptimal. So remember, in the vertex cover, we did whatever we are forced to. If you have a high degree vertex, that must be there in any k size solution, so I picked it. So if you can guarantee that a cut vertex must be there in any k size solution, then no problem. I can justify it by including it, but that I can't say. I can remove degree 1 vertices. They don't play any role, right? But after that, even coming up with an FPT algorithm for this problem is not easy. Okay, so there are two things, right? Even though both are same, fixed parameter tractability and kernelizability notions are the same. Sometimes it's easy to come up with the fixed parameter tractable algorithm, right? You can just do some branching kind of a thing. But even designing an FPT algorithm for this problem is not easy. Coming up with the kernel is even harder. But we'll get to all of that at the course of the lecture. But I just want to point out that everything is not easy. In particular, there are a lot of nice combinatorial graph, classical graph theoretic theorems are used to come up with some nice kernel for this. Okay, we'll do that in the next 2-3 lectures.
So what is exactly feedback vertex?
It's a set of vertices whose removal makes the graph acyclic. That's what I'm telling you, right? So S is an FPS if G minus S is acyclic. Right? Can you say this similar statement for vertex cover? S is a vertex cover if G minus S is edgeless, independent, right? So here you want to cover all edges, vertex cover. Feedback vertex cover covers all cycles. right? So you can remove isolated vertices, remove degree 1 vertices, but after that, we are stuck and we need to come up with a good bound, not very clear. But suppose I tell you that the graph is caudal. What is a caudal graph? So a G is caudal if what's the definition? You know what a caudal graph is? If G does not have an induced cycle of length greater than or equal to 4. Right? What is an induced cycle? Well, this cannot be a subgraph in the graph. If you have such a cycle, one of these edges must be there, right? Either this edge or that edge. Every large cycle should have a chord. Okay, so this is a chord, which means an edge joining the non-adjacent vertices of a cycle. So in a chordal graph, how does an FVS look like? What do I need to cover? Of course, I mean feedback vertex means I need to cover all cycles. But can you say a little bit more? Yeah, it is enough to cover all triangles, right? If you make sure that every triangle is covered. So you have a set of vertices that clearly triangle has to be covered because that is also a cycle and your S should cover that cycle. But covering such one direction, covering cycles is enough because you suppose you covered all cycles and you still left with some large cycle from which no vertex has been picked in set S. Well, your graph had this cycle, this triangle. What did you do? I mean, we must have picked one of this. Okay, so it's an easy exercise that S is an FES in G. S covers all triangles in G. Okay, so what? Does that make the problem easier? Well, in the vertex cover, we were trying to cover every edge. Every edge is like a 2-element set. Now we are trying to cover every 3-element set of this. Somehow you can think of it more generally as the following 3-heating set problem. Okay, so I'll give you this FPT or the kernel, nice kernel for feedback vertex set by generalizing this vertex cover. Let's understand what is happening in vertex cover, and you see that the same idea will work more or less for what is called a 3-heating set, which can be used to give a kernel for feedback vertex set in caudal graphs. In general graphs, it's a whole new game and it requires a lot of work. Okay, what is a 3-heating set problem? The input, is that problem? You can ask them to mute it, maybe is that problem. Okay, you have a question or? No, okay. So maybe you can put your mic on mute if it is not. It is in, okay. So the input contains a pair, U and the family. U is the universe let's say it's some 1, 2 up to n. F is a family of 3 element subsets of U. Okay, my parameter is some integer k. And the question is, so is there a subset S contained in U, cardinality of S is less than or equal to k, such that S intersection F is non-empty for all F in F. Okay, so for example, I may have U would be 1. So U may be the 1 to 6 and this may be a family of 3 element sets. Now what I want is I want a small sized subset from here which will intersect every set. Okay. So what kind of a hitting set can you get here?
3, 1.
3, 1 intersects everybody?
Yes.
Okay. So 1, 3 is a hitting set. Okay, it should hit every set. Your input is a universe and a family of sets. And I am looking for a subset of the universe that intersects every set in the family. This is an NP-hard problem. Yeah. Can you model vertex cover as a hitting set problem? I am just saying that this is a generalization of vertex cover. So given a graph where I am interested in finding k vertices to cover all edges, create a U comma F such that there is a hitting set of size k if and only if G has a vertex cover. So what should be the universe? What should be the family of sets? Right. So G has a V K.
U is V, F is E.
So U, the universe is my vertex set. F is E. F is a family of sets. So what?
So
The
pair of
set is
That's it.
U.
Yeah. So my F would be sets U comma V, where U V is an edge. Okay. So you have a vertex set is my universe, and pairs of the endpoints of the edges form my family. Now I want to hit it, hit every set. I want to cover every edge. I want a subset of vertices that will intersect every edge. So vertex cover is essentially a 2 hitting set problem. Now I am saying let's generalize to 3 hitting set. Yeah.
So we can't see the area of the board where you're writing. Can't see the right part.
Okay. Can you see it now? Good. So we produced a kernel for 2 heating set really, because if we will go and simulate what did we do for vertex cover. It's essentially a k-square vertices, elements and k-square size family, k-square to k-square kind of a kernel in polynomial time. We reduced an equivalent instance. Now I am just saying, oh, can you do it for 3 heating set, or more generally for a d heating set? And note that FVS in caudal graph is essentially a 3 heating set problem, right? Because you write down vertices of triangles, and now I want to hit every triangle. So there are only n cube triangles, so it's all polynomial time reduction. Now I want the k size thing which hits every triangle. Okay, I want to get a kernel for it. So all I'm saying is, okay, you want to solve, but I can't say the same thing for general feedback vertex set. Why? Because I have no bound on the size of the cycles. Because it's caudal, it was good enough to hit only the triangles, and that was like 3 sizes. But if I have to hit the vertex set of every cycle, I don't have any bound, and this hitting set problem is hard even in the parameterized world if there is no bound on it. Okay, so that's not the route for solving the general feedback vertex set problem, to which we will come to that later. But for now, I can, for example, solve caudal feedback vertex set by appealing to my 3 heating set. So now let's apply a similar idea for 3 heating set, right? I have a family, I have a universe and a family of 3 sized sets, and I want to get some k vertices that will intersect all k elements of the universe that will hit every family, every set in the family, right? So let's apply some obvious reduction rules. Recall the reduction rule we applied for vertex cover, which is essentially isolated vertices. What does that mean? Some vertex that doesn't participate in any edge at all, get rid of it. Sure, which we will assume it is not even the case, right? That every vertex is in some set. Otherwise, you can get rid of that vertex from your universe clearly. We appeal to this. If a vertex appears in more than k sets, right? Remember, vertex cover was 2 heating set, right? So I have a family of sets of size 2, and I said if you have a vertex that appears in more than k sets, if you don't pick that, to hit these sets, since all these sets are distinct, you have to pick more than k different elements, and that was not enough, so we forced my vertex into it. Okay, so if I want to apply a similar kind of a rule, what should I do?
Remove all the k plus 1 or whatever sets that contain the vertex.
No, what vertex? What are you talking about now? What is it?
If the element occurs in k plus 1 or more sets, remove all of them, reduce k by 1. This will directly give you a bound.
You're going to pick that vertex to hit it, is it? That's what you're saying.
Yeah.
Why should it be necessary? It's not clear. In the vertex, yeah, the other guys may intersect a lot, and you may be better off picking one of those vertices to hit these sets. So you're saying if a vertex appears in more than k plus 1 or more than k of these triples, that vertex is forced into the solution. That's not obvious here. It was obvious for 2 heating set. You guys know? So, okay. No, let's not do one element. Let's look at a pair and then argue this. Okay? Then it's very easy, right? So, rule 1. Similar to the, so by the way, that vertex cover kernel I talked about is due to Samuel Buss. So sometimes that is called the Buss rule. Okay, you have a high, some vertex which has high degree, you have to pick that kind of a rule. It's called the buzz rule, okay? Because it was applied first to vertex cover. So what you do is apply this buzz rule for pairs. So if there exists a pair x comma y that appears in greater than k sets, then what can you do? You can't get rid of it. I mean, what can you conclude? Yes, what? X or y must be in the solution. You can't force either one, but you are clear that x or y must be in the solution, because if you don't pick xy, to hit each of the sets you have to pick distinct elements, right? So what I am saying is I have x comma y some a1, x comma y a2, where L is greater than k. So this is how sets are, and this pair together appear in more than k sets. If I don't pick xy, I don't pick x or y, then to hit this set I have to pick a1, to hit this set a1, a2, and that is more than k of them. So x or y must be in the solution. So what should be my reduction rule? See, this is very, very clever. See, even if you know the consequence, what you want, how do you create your gadget is not sometimes obvious.
Conflict. Add a separate set containing each.
Exactly. Add a set xy and you can get rid of these, right? So get rid of these sets and say I'm going to add to my family x comma y, because all I'm saying is please hit this set along with all other sets you have. Don't bother hitting this, because hitting this will also hit all these sets. So the reduction rule is remove the sets containing x comma y and replace with all sets containing the pair xy is removed and replaced by this single set. Now, S, if and only if S needs to be proved, but that's obvious, right? Because similar to that bus kernelization rule, that x or y must be picked. If there is a chance of maybe there is no k-sized solution at all, then I can't say x or y must be picked, but that's okay. I mean, all saying, if you want a k-sized solution here, you better find a k-sized solution here. So you have to pick x or y, and then if you do that, you are going to intersect all of this, replace it. So you're removing a lot of sets and replacing by a single set. So you keep applying this rule again and again and again and again. At the end of it, now what can you say? Every pair appears in?
At most k.
Yeah, at most k sets. That's all you can say, right? This rule is not applicable means that every pair appears in at most k sets. Okay, good, right? So now you do this reduction and you got your new family. Maybe even a new universe. How will you reduce the size of the universe? I mean, I'm not going to remove A1, A2, AL because they may be appearing somewhere else. But when would you remove them from the universe?
When they are isolated.
When they do not appear anywhere else, then you might as well get rid of them from the universe as well, right? So that's maybe a rule 0. If an element doesn't appear in any set, remove it from my universe. I mean, I didn't put that rule because I said initially we assume it is there, but at the intermediate stage it can happen. So you keep applying these rules, and these are all polynomial steps because you look at every pair of elements, run through your family and count the number of sets it contains. These are some n square, n cubed kind of time. So at this point, so now every pair appears in at most k steps, k sets. Good. So now
Now k prime to k minus 1.
Now you
no, because I have not picked anything yet. So I can't change k because I change k only if I picked something into my solution. I have not done that. So k remains k.
No, G is remains G.
I mean f, the UF family, that has changed because I might have removed some vertices from the universe, I have removed some sets from the family, got a new family and all that, but I have not picked up any element into my solution yet. Okay. So now, okay, I have to cover this with now k sets, right? Okay, you said something.
same
What?
thing as before.
Like
N
what?
choose 2 times k is greater than or equal to n choose 3. N is the universe.
You need a rule. So what's the rule you want to see? From that you have to deduce a rule. Okay. So what I want to say is the following. I hope this is correct. If a vertex, if an element appears in, is this correct? In more than k square sets, right? Yeah, good. So that's sort of the rule from what you're saying. So just maybe that's more intuitive. So tell me what you're saying.
So now
So you're saying size of f
is
at most.
is at most n choose 3.
That was always the case.
Yeah.
After the reduction rule, what can you say?
Now this size must be less than or equal to n choose 2 times k.
Good. Right? So this is here. More or less like that, no? I mean, it was size of the family was n choose 3 to start with because that's the maximum 3 element set. But now, since any pair appears in at most k sets, the size of the family would be at most this much, right? We've reduced it. Why? So is it? How do you prove this? Because there are n choose 2 pairs and everything appears in at most k sets. Yeah, even assuming they are all distinct, right? This is actually already an overcounting, but this is an upper bound. Okay, so what?
No, I was assuming that.
Okay. So this is a useful observation, but let's just look at it. So suppose if an element appears in more than k square sets, then like the bus rule, now I am going to say that it is forced into my solution. Why? Because, so here is some element x it appears in more than k square sets. Then if suppose I do not pick this into the solution, then I have to pick one of each, one of these guys. Yeah, so here is the thing. Suppose I remove x, suppose I don't pick this into my solution, then I have to hit this pairs, right? But some of these pairs may be duplicates, so it's easy. If I hit one, I might intersect. But how many duplicates can there be, right? You know that this is at most k. One pair can appear at most k because of this rule, right? So, since if this number is more than k square, what does that mean? I have at least k plus 1 pairs.
K plus 1 elements will have.
Is that clear? Because they might intersect. No, they can't intersect. Okay, because x with an element. Okay, so I need to argue a little more carefully. I just want to say this: if an element x appears in more than k square sets, then x is in any k element solution. Okay, let me put a star here. We'll come back to proving this. Yeah, so I mean you can actually appeal to bus kernelization kind of a thing. Remember, so look at, so this has more than k square edges, okay? Think of, this is like a graph now, right? Because these are pairs, k square edges. Now, any vertex can appear, has degree at most k. Why? In this graph. X and that vertex is a pair which cannot appear in more than k sets, because x is appearing in every set, right? So suppose I look at this vertex, x along with that vertex, so this vertex in particular cannot appear in more than k sets, because otherwise this pair appears in more than k sets. So when I remove this, every vertex is degree at most k. Okay. And same as the bus argument. Every vertex has degree at most k, and if I have more than k square edges, I cannot cover with k vertices. Right? So if I have a chance of a k size solution here, I better include x. Okay. I'm not writing formally, but this is all part of the proof, right? So since every pair appears at most k sets, if I remove x from these edges, every element is degree at most k. And since there are more than k square edges, k vertices cannot cover all these edges, because I am looking for a solution of k elements. So that means x in any k element solution. So I pick x into the solution. So this implies that I take my S is equal to S union X, and K becomes K minus 1. Now keep applying this rule again and again. At the end of it, now what do you have? Every element appears in at most K sets. Okay, now are we done? It's now again it's like Buzz's rule, right? Somehow if I bound the frequency of every element, then, and I'm looking for a k size solution here, right? I have this new family. Every element appears at most k square times, sorry, not k sets, k square. every element appears in at most k square sets. I am looking for a k-sized solution, but so any single vertex into the solution can intersect at most k square sets, because any element appears in k square sets. So any single element of the universe can intersect in at most k square sets. So if you are looking for a k-size solution, if you have more than blah many sets, the answer is no. What is blah? K cubed, right? If you have more than k cubed many sets, you simply say no, because there is no k-size solution. Any k elements of the subset can intersect at most k cubed many sets. So if f is greater than k cubed, return no. Now we have a kernel. I produced a family whose size is at most k cubed. Universe size is at most 3k cubed, right? Because all these sets can be disjoint. If an element doesn't appear in any set, you would have gotten rid of it in rule 0. So finally, f is at most k cubed, and the universe size is at most 3k cubed. Okay, so this solves, essentially it's the bus rule. Applying it a couple of times, it solves the more general 3-gating set problem. It solves F feedback vertex set in caudal graphs. It solves feedback vertex set in what are called tournaments, right? Same argument. Directed feedback vertex set in tournaments has a kernel with order k cubed vertices So what is a tournament? It's a directed graph with exactly one directed edge between every pair of vertices. Okay, so basically take a complete graph and give some orientation. So no, there is more, right? I should add 2 and 5 and 3 and 1. So take a complete graph and each edge gets an orientation that is called it's a special kind of a directed graph called tournament. So this feedback vertex set question makes sense even in directed graphs where you want to cover every directed cycle. Okay, so you want to pick k vertices whose removal makes the resulting graph devoid of directed cycles. And for general directed graphs, the FPT algorithm took a long time and we still do not have any polynomial size kernel. We do not know whether it exists or not. It's a major open problem. But this is a special directed graph in tournaments. Why do we have a k cube size kernel? Because just like caudal graph, it's enough to hit every triangle, right? Because of this simple observation a tournament has a directed cycle if and only if it has a directed triangle. So you just go through your tournament, pick, look at triples of vertices, find triangles, collect your set of vertices, formulate a 3 hitting set instance, apply this kernel, you get a k cubed kernel. Okay. Well, there's one little. Okay, what's the proof of this? It's pretty easy. How do you prove this? If you have a triangle, you have a directed cycle. But if you have a directed cycle, there is a triangle y. Suppose you have a large directed cycle. Remember,
Because of the
tournament definition tells you that there is a directed edge between every pair of vertices. So I ask, how is this edge? There must be an edge. If it is this way, good, you already got a triangle. No, if it is this way, now I am going to ask, what about this edge? Right? If it is this way, you got a triangle. If it is this way, you got a triangle this. So if you have a large cycle, you will always have a triangle. So it's enough to cover all triangles. And so you formulate a hitting set instance and use the kernel. Okay. There is one little thing. My kernel definition set that I take an instance of the problem in polynomial time, produce an equivalent instance of the same problem such that whose size is k cubed or whatever you want to show. Now here, if I follow through this hitting set route, I start from a tournament, formulate a hitting set, kernelize it, and I get a family of triples with k cubed sets and 3 k cubed vertices. Then you have to turn that into a tournament, right? Finally, I want to produce an instance, equivalent instance of a tournament feedback vertex set. So it's not immediate that you can convert this family to a tournament. But I mean, okay, there is a way around it. So if I don't care about k cubed runtime, but some polynomial kernel size, then there is an NP complete. This is an NP complete problem. That's an NP complete problem. So there is a polynomial time reduction from hitting set to tournament feedback vertex set. Apply that reduction. There is no n here anyway. So this k cubed will go to something else, but it might become some other function of k. Okay. As long as you are happy with the polynomial size reduction, you can just do that NP complete reduction. But if you want to stick to k cubed, you may want to do some gadgetry to get there. Okay, just want to make that remark. Now, next question is, if I want to come up with the kernel for a D hitting set, for a larger D. So here, remember, for 2 hitting set, which is vertex cover, our kernel size is like k square. For 3 hitting set, k cubed. So not surprisingly, for a D hitting set, the kernel size is k power d. But how would you show this? You can apply something similar, apply induction. We'll do that next time. And what we will use is this nice theorem by Erdos and Rado called sunflower lemma. And if you apply that, you will get a trivial k power d kernel, okay, for a D hitting set. Okay, so we will continue next time.
Maybe there's a way of showing without using this.
You can. I mean, in fact, all of this can be cast into sunflower lemma.